Hello and welcome to section 3.1 notes. It's all about extrema in chapter 3. We will be discussing relative extrema and we will be discussing absolute extrema. Relative or local extrema, you're basically just talking about the highs, the lows. So relative or local minimum, they'll be using that interchanging. So the relative or local minimum, those are going to be the low spots of your function. So for instance, if we have something like this, relative minimum are the low spots, that little guy right there. The relative or local maximum, those are the high points. And of course you can see why we would want to know those extrema. If you're talking about a profit function, you want to know those relative maximums. In a cost function, you'd like to know what those relative minimums are. Looking at this little example here, this is a pretty healthy looking little equation. But you're looking and you can see that there are high points, there are low points, high points, low points, etc. When we look at this, we're going to be checking for critical points. Points are where the graph changes, where there are possible extrema. Basically, the definition of a critical point is where your derivative is equal to 0 or where it's undefined. Now, 0 means there's a nice smooth curve. There's a nice transition. So when I'm looking at where my derivative is equal to 0, I'm looking at this point right here, this point, and this point. So those 3 points in red would be critical points. When we're looking at where the derivative is undefined, remember your derivative is undefined at corners, cusp, vertical tangents, and discontinuities. So my derivative is undefined right here, right here, also right here at 1. Those are all places where I am undefined. Now, when you look back at this definition of a critical point, it says points where graphs change, where there are possible extrema. So notice we do have extrema here at 1, 2, 3, 4, 5, -5, -2, -1. Those are all extrema. At +2, at +4, those are all extrema. But notice where I was undefined because I was discontinuous at 1, that would not be a relative extrema. We're going to be looking at the extreme value theorem. And just like the intermediate value theorem, I believe this is named perfectly. Extreme value theorem means that extreme value. Where do you have the absolute highest point and the absolute minimum point? Okay, so the extreme value theorem starts off. First of all, f is continuous on the closed interval. F has to be continuous. So aren't you glad we discussed continuity before we did this? So you have to be continuous on this closed interval. If you are continuous on that closed interval, then you will have both an absolute minimum and an absolute maximum. You will have a high point and a low point. Now, these maximums will occur at endpoints or at critical points. Now, what that might look like is you might have something like this. We are continuous from A to B. My high point would be here at B. My lowest point would be here at A. So that would be at our endpoints. We may also have something that looks like this. We've got B, we've got A, and here we have C. We do have a low point, it's at A, but this time my high point is at C. that is going to be a critical point. Okay, so these extreme values, those absolute mins and absolute maxes, are going to occur at endpoints or at critical points. So in order to find absolute extrema on closed intervals, closed interval, not open, closed, so we're looking at the brackets. Okay. The first thing you're going to do is find the first derivative. Then you're going to find critical points by setting that first derivative equal to 0 or finding out where it's undefined. When you're finding these critical points that come from undefined, you have to make sure that that point that you find is in the original graph. The third thing you're going to do is you're going to find the y value at all of these critical points and at all those endpoints. The smallest value is going to win absolute min. The largest value is going to win absolute max. So let's see what this is going to look like. They want us to find the absolute extrema. They've given me the equation 3x to the fourth minus 4x to the third. I have a closed interval. So I already know I am guaranteed to have an absolute min and an absolute max. First thing we're going to do is find the derivative. The derivative of 3x to the fourth is 12x to the third. The derivative of 4x to the third is 12x squared. This is a polynomial, so there's no place where my derivative is undefined, so I'm going to go ahead and set it equal to 0 and find those critical points that come from where my derivative is equal to 0. Factor out of 12x squared, and then I have x to the 1 power minus 1 left. If I set each factor equal to 0, I'm going to have critical points at x equals, well, 12x squared equals 0 when x is equal to 0, x minus 1 equals 0 when x is 1. So I have two critical points I need to check. Both critical points are in my interval. I am going to find f of -1, f of 0, f of 1, and f of 2. Notice you found the derivative finds you those critical points, those other possibilities. In order to see who wins the absolute min, absolute max, you've got to find the actual y value. So you are going to go back to the original function, That's going to give you the y values. Well, when I put -1 into the original equation, I get -7. When I put 0 in, I get 0. When I plug 1 in, I get -1. When I plug 2 in, I get 16. Just looking at the y values, you can see that we have a winner at absolute max. I need to write it out, though, in point form. So my absolute max is right here at 216. The max occurs at 2. That maximum value is 16. My absolute min is right here. So my absolute min occurs when x is -1, and that minimum value is -7. Make sure that you are showing both in point form. You have some examples for you. This video is very short, so I'm going to go ahead and do those examples on this video. So at this time, if you just stop your video, work those examples, and then just start it up again, we'll work them through together. We're on a closed interval, so we want to find the derivative. Notice I have a little chain rule here. Taking the derivative of 2 sine is 2 cosine. The derivative of the cosine of 2x is negative sine of 2x. You've got the negative already, so that's going to change that. Times the derivative of the angle. A chain rule, derivative of the trig function times the derivative of the angle. When I look at this, I have a double angle here and I have a single angle. I want them all to be the same angle, so I am going to change my sine of 2x into 2 times the sine of x, cosine of x, using my double angle formula. Now this becomes 2 cosine of x plus 4 sine of x cosine of x. There's my first derivative. When I go to set this equal to 0, I am going to factor out what they have in common, which is a 2 cosine of x. I end up with 1 plus 2 sine of x inside. I'll want to set each one of those factors equal to 0. So I'm looking for where cosine of x equals 0. I'm looking for where sine of x equals negative 1/2. Well, cosine of x is equal to 0 at pi over 2 and 3 pi over 2. We don't need to go any further because we are on a closed interval. We don't need to consider anything outside of that interval. Sine is equal to negative in quadrants 3 and 4. You're looking for an angle that has a reference angle of 1/2, which is your pi over 6. So the angles we're looking for are 7 pi over 6 and 11 pi over 6. Whew, we got a lot of angles to look for. Those are the possibilities along with your endpoints. So we're going to find f of 0, and you can put them in any order you want. So I'm just going to flip them in there. Sometimes I like to put them in order just to kind of keep the flow of things, but it really does not matter. Whew, there's a lot of them. Remember, you're plugging these critical points and the endpoints into the original equation. You are finding that y value. Well, when you plug 0 into the original equation, this guy right here, 0, you get negative 1. When you plug in 1/2, you get 3. 7, 6, you get negative 3/2. 3/2, negative 1. Negative 3/2. And then 2 pi, you get your negative 1 again. With trig functions, there's a lot of extrema going on. So there's a possibility you could have multiples of maxes or multiples of minimums. Remember, you are looking for the absolute, so they would have to tie. Let's look at our absolute max. Look for the highest y value. Oh, looks like we have a winner. Absolute max at pi over 2, 3. Absolute min. Looking for the lowest value. Oh, looks like we have a tie. It's exactly the same value. So 7 pi over 6, comma, negative 3/2, and 11 pi over 6. Negative 3/2. You will have an absolute min and an absolute max if you are continuous on a closed interval. Try the next example. Remember to pause the video so that you can do the work and then check it when you're finished. Okay, so my derivative. The derivative of 2x is 2. The derivative of negative 3x to the 2/3 is 2x to the negative 1/3. So that's 2 minus 2 over x to the 1/3. We definitely want to get a common denominator this time. Sorry, but common denominators are going to make our life easier. I know you don't believe me, but it's true. There's my first derivative. Because I have a fraction, I do have places where my derivative is equal to 0 and where my derivative is undefined. My derivative is equal to 0, and I always like to put it there, derivative equals 0. That's where your numerator equals 0. If I solve that, if I divide both sides by 2, I get 1/3, x to the 1/3 minus 1 equals 0. So x to the 1/3 equals 1. So x equals 1 is my first critical point. 1 is in my interval, and it is okay in my original equation. Now I'm going to look to see where my function, my derivative is undefined. That's going to be where my denominator is equal to 0. Well, x to the 1/3 is equal to 0 at x equals 0. 0 is in my interval here, and it is a point on my graph. You've always got to watch those derivatives that are undefined. Make sure the point you find is a point in the domain of your original function. And everything is perfectly fine for us. So we're ready to plug in our numbers. So f of -1, f of 0, f of 1, and f of 3. When I plug in -1, I get -5. When I plug in 0, I get 0. When I plug in 1, I get -1. When I plug in 3, I get a decimal. Make sure you take your decimal to 3 decimal places. I have an absolute min at -1, -5. I have my absolute max at 3. 3.240. Okay. So that time we had an extrema that came from where our derivative is undefined. Now the reason why that is, where you're undefined, remember you have a corner, cusp, discontinuity, and a vertical tangent. Only a corner or a cusp can grow up to be an extrema. Your corner, that can be a high point. Your cusp, that can be a high point. Discontinuity can't be. Vertical tangent also cannot be. So that's why you really have to pay attention to when you are undefined, are you an actual point on the graph? Because you can have extrema coming from those undefined derivative points. All right, this completes 3-1. I'll see you tomorrow.